Each one of us is a treasure trove, a unique combination of talent and potential. In today's hectic world, where being the same is the norm, we need to stop for a moment to encourage individual distinction. At the Galileian School of Higher Education, brilliant people meet and inspire each other in common spaces. Places where everyone's value can become a collective experience to be shared with the world. Here, each student has their own voice, role and impact. And from the humanities to natural and social sciences, love for learning is encouraged and fostered through critical thinking. Intelligence must be looked after and cared for. The teachers and tutors at the Galileian School work with enthusiasm and skill to guide each student as they explore their own personal path. Distinction is better than perfection. Discover your distinctive talent at the Galileian School, where each student has the chance to shine in their own special way.
Good afternoon and welcome to the Galileian lecture. My name is Gianguido Dall'Agata and I am your host this afternoon. I am the director of the Galileian School of Higher Education who's organizing this event. The Galileian School is the excellent school of the University of Padova, and it hosts some of the best and brightest students of our university, providing them some training opportunities and a varied and stimulating cultural environment with a special focus on interdisciplinarity. Since its foundation, the school has also always tried to offer moments to share knowledge and engage in dialogue with the greatest minds of our time, like in today's event. So I'm therefore very grateful to Professor Dijkgraaf for accepting our invitation to deliver the Galileian lecture. Before getting into the lecture, let me yield the floor to Professor Zwirner, who will bring the greetings from the rector and the university, and is going to introduce the speaker. Please, Professor Zwirner.
So, good afternoon and a warm welcome to our distinguished speaker and to the audience, also on behalf of our rector Daniela Bappelli, who cannot be with us today. As those who were present at the previous lecture know, this Galileian lecture is part of the events honoring Gregorio Ricci Curbastro in the 100th anniversary of his death. 104 years ago, on the same day and in this very Aula Magna, Einstein gave a famous lecture on general relativity in which he acknowledged the role played by the absolute differential calculus, called today tensor calculus, invented by Ricci, also in collaboration later with his former student Levi Civita, in the mathematical formulation of his theory. Earlier this afternoon, we heard in another lecture by Professor Rosanna Tazzioli that the historical aspects of the interplay between fundamental physics and mathematics at the times of Einstein and around. This lecture will explain how such interplay takes place at the forefront of present-day research and introduce a novel perspective anticipated by the title, The Unreasonable Effectiveness of Modern Physics in Mathematics. We're very grateful to the Galileian School and its director, Professor Dall'Agata, for having suggested and sponsored this event. And of course, we are especially grateful to Professor Robbert Dijkgraaf for having accepted our invitation and for being with us today. He has already an indirect link with Padua, since his PhD supervisor, Nobel laureate Gerhard Hooft, is a honorary citizen of our town. We are very glad to have him now in person, besides indirect links. Robbert Dijkgraaf is a mathematical physicist whose research focuses on the interface between mathematics and the physics of the fundamental interactions. He gave outstanding contribution to string theory, and for his contributions to science, he was awarded the Spinoza Prize, the highest scientific honor in the Netherlands, in 2003. After spending several years in Princeton, he became professor at the University of Amsterdam in 2005, where he still serves today. He has a prestigious record in science policy and advice. He was president of the Royal Netherlands Academy of Arts and Sciences from 2008 to 2012. He directed the Institute for Advanced Studies in Princeton, one of the top world centers for theoretical research and intellectual inquiry from 2012 to 2022. And he recently served as Minister of Education, Culture and Science of the Netherlands from 2022 to 2024. By the way, this civic engagement also reminds of Ricci Curbastro, who was part of the Padua city government for a number of years. Last but not least, Professor Dijkgraaf has been very active in science communication and public engagement. He regularly writes for the national press. He's a very popular guest of TV shows, and he has promoted and supported a website with daily experiments for kids. Since we are all eager to listen to the lecture, I won't take more of your time and leave the floor to the chair and to Professor Dijkgraaf. Thank you.
Thank you so much for the kind invitation. A great honor to speak here in this most beautiful lecture hall I think that I will ever speak in. So this is an absolute delight. And it's a particular delight to speak here in the University of Padova. My own university, the University of Amsterdam, was founded in 1632. And it's amazing to think that the University of Padova was older then than my university is now. In fact, when it was created in 1632, it was very ambitious, and one of the first job offers they made was to Galileo. He was certainly movable, but he wrote back that his health didn't really allow him to travel to the Netherlands, so history took another course. I'm very eager to tell you a little bit more about the interaction between the two fields that I think most of us relate to, physics and mathematics, and their interaction, and it's very much captured both by the distinguished contributions of Galileo and Professor Ricci Curbastro. But I want to begin with my title. The unreasonable effectiveness is actually a phrase first coined by Eugene Wigner, the Nobel Prize physicist, who wrote an article in 1960 about the unreasonable effectiveness of mathematics in the natural sciences. And he explains this effect that math has this unique opportunity to capture many parts of the real world with an anecdote. Let me slightly rephrase it. It's an anecdote where a mathematician meets a shoe salesman. And the shoe salesman says, no, I have to buy all those shoes and I never know in which size. And then the mathematician says, oh, it's very easy. There is the Gaussian distribution, and he shows him the formula of the Gaussian distribution. And then the shoe salesman says, what's this in this formula? What's this funny symbol? I say, well, that's the Greek letter pi. What's that? Well, it's the ratio between the circumference and diameter of a circle. And then the shoe salesman says, what do shoes have to do with circles? And it's quite remarkable that in this, so it's even square root of pi. So think about how pi entered in this equation, and it's a good exercise to go in your mind. So it's a wonderful property that math has this ability. And of course, there's a long history of particularly physicists explaining their love of mathematics. So Galileo, and he's looking at us, quite sternly there, he wrote this wonderful metaphor that, like, science is reading this book of nature. And in order to read the book of nature, to have to learn the language in which it was written. And according to Galileo, it was written in the language of mathematics. which in those days was mostly Euclidean geometry, so triangles, circles, and other geometrical figures, without which it's humanly impossible to understand a single word. In fact, this view has a long history. For instance, this is Arnold Sommerfeld, one of the famous physicists of the early 20th century. If you want to be a physicist, you must do three things: study mathematics, study more mathematics, and do the same. And I think this is still a lesson that we often teach our students. To go in a slightly more modern age, here's Richard Feynman. To those who know mathematics, it's difficult to get across a real feeling as to the beauty, the deepest beauty of nature. If you want to learn about nature, you have to understand the language that she speaks in. On the other hand, Feynman is also famous by saying that if all mathematics disappeared today, physics would be set back exactly 1 week. Now, I always thought, well, this is a very smart remark, until I heard the response of the famous mathematician Michael Atiyah, who said, this was the week that God created the world. So I say 2-1 math, physics. But there's this other nice quote. This is, that mathematics is capturing the world, and we will talk about it, but it's capturing much more. So Jean-Pierre Serre, famous Fields medalist, French number theorist, geometer, said, the other sciences search for the rules that God has chosen for this universe. We mathematicians search for the rules that even God has to obey. So the laws of logic, all possible laws of nature. And in fact, there's a long history of mathematicians trying to capture all of physics. Hilbert, when he had his famous problems at the turn of the last century, number 6 was the mathematical treatment of the axioms of physics. So the idea that just as you have the axioms of number theory, of Euclidean geometry, what are the axioms of physics, and can you build up physics as you build up mathematics from the ground up? Now there is this kind of interesting kind of logical paradox I'm going to share with you. It's first was brought to our attention by Roger Penrose, and he had this impossible triangle. So if we start, say, with the physical world, then the physical world describes everything around us, including our brains, including our thoughts. So the mental world is a small part of the physical world, because just we are biological computers. And then in our mental world, that also includes the minds of mathematicians, then create then a Platonic mathematical world. But this Platonic mathematical world, as Sarah was saying, contains a small part, which is the physical world. And you can go around and around and around. So there's this like impossible triangle, where somehow nature, say science, mathematics, and what we think about are in this very complicated relationship. And I want to explore this further with you. Now, there's a long tradition of, so the question is that we will answer, is mathematics inspiring physics, or is physics inspiring mathematics? And in that dialogue, which direction is information flowing? And although mathematics has this kind of Platonic idea, it's also in some sense an environmental science. So let's go through important examples in the past. So clearly, if you think of ancient geometry, it was clearly created partly by, the very practical reason of understanding the motion of the heavenly bodies, measuring land, and so that Euclidean geometry fled out of it. Another good example is calculus and analysis. It was created by mathematical physicists like Newton and Leibniz, understanding the laws of objects as they fall and float and move, led them to study infinitesimals, analysis, and the whole differential calculus. Or think about algebra. Though symmetric objects were around already in the time of the Greek, it's kind of interesting they never invented group theory. And it took to kind of algebraists and solving, Galois and Abel solving the quintic equations that led to the birth of group theory. So this is kind of interesting way in which mathematical concepts emerge out of practical consideration. Now the topic today, which is to a large extent the work of Ricci Curbastro and his levi civita, as we heard in the first lecture, about understanding Riemannian geometry, differential calculus, etc., has an interesting relation because it was there first. And as we heard earlier, out of this it led Einstein and his mathematical friend Marcel Grossmann to develop the theory of general relativity. Einstein was definitely not a great lover of mathematics. No, I think he felt it to a large extent to be kind of abstract nonsense. He was a very, very intuitive and geometrically thinking, but when he was confronted with the work of Ricci Curbastro, he said here, now, this is a quote of one of his letters, "I'm working exclusively on the gravitational problem. I believe I've overcome all difficulties with a medical friend of mine," which was Grossmann. "But one thing is certain, never before in my life I've troubled myself over anything so much, and I've gained enormous respect for mathematics, whose more subtle parts I considered until now in my ignorance as pure luxury." That's putting it kindly. "And without this problem, the original theory of relativity, that special relativity, is child's play." It's really an advanced piece of mathematics that actually was ready there to be used. That's quite uncommon, that as a physicist, you want to solve a deep problem. And mathematicians were therefore. There's a beautiful quote by Steven Weinberg, the Nobel laureate. He says, "It's a spooky quality of the ability of mathematicians to get there ahead of us. It's when Neil Armstrong first landed on the moon and he found in the lunar dust the footsteps of Jules Verne." So the imagination of mathematicians thought about laws of nature and structures that before those laws were even the object of study in physics. So we can ask, what is the nature of mathematics? And I want to share with you a line of thought that I find very inspiring. It's in a piece that the famous the geometer Bill Thurston wrote in an article called "Unproven Progress in Mathematics." And he raised the question, what is a piece of mathematics? So take something that is part of any vocabulary in physics and mathematics, the derivative. So what do you mean if you talk about the derivative? What is the right definition? And Bill Thurston starts by saying, well, you have the first definition that you learn in former calculus, the so-called epsilon delta definition. And quite remarkably, in the published article, he writes it wrong. But then he says this is a formal definition. It doesn't capture some intuitions. For instance, it's also the velocity. And once you start to think of a derivative as velocity, you see, wait a moment, it can have a certain direction, like velocities in everyday use. So it can be a vector. So you can also differentiate something that is a vector instead of a function. You can also think of it as a slope, so the tangent to a surface, for instance. And then you see, wait a moment, it's easy to think of a derivative of more than one variable. Or you can think of it as infinitesimal, as Newton and Leibniz did, so small variations. Or you think of it discrete, think of it as a discrete approximation. Or you think of it as symbolic. I think that's many ways in which you learn calculus in a very practical way. So you differentiate certain functions. Or you think of it as the linear approximation. Many problems you can approximate them linearly, and it leads you very naturally to the first derivative. Or you can think of it microscopic. Take any behavior and look through a very powerful microscope, of course. Then at some point you get you get all these other different things there. And these are all good points. When he then goes on, at some point he has definition 37. I won't read it. But he said, there was a moment in my life when I needed definition 37. In fact, there are other ways. For instance, I'll at some point say something about knot theory. There's the notion of a derivative of a knot. So what my point is, a mathematical concept is all of this to all of you. It has these various different kind of components. So it's environmental, but there are various kind of environments. I would think of it a little bit like a diamond, that many facets. And depending on which point of view you take, a certain aspect will light up. Now, what guides mathematics? So mathematicians often talk about beauty, both mathematicians and physicists. And this is the famous line of Keats, beauty is truth, truth is beauty. In fact, in the article of Wigner about the unreasonable effectiveness, he starts with this quote of Bertrand Russell, where he says that mathematics has this kind of supreme beauty, cold and austere, without, beautiful words by the way, the true spirit of the light. That's something that really focused a lot of mathematics. If you think about what Ricci was doing, it was remarked, there was no application inside. He just developed the formalism because he loved the formalism, the power of the mathematical concept. So beauty is an important guidance. You know, Hermann Weyl, who was a great mathematician and a great mathematical physicist, when he was asked if you had to choose between truth and beauty, what do you choose? He was very clever. He said, well, try to have both. But if you really had to force me, I chose the beautiful over the true, which is an interesting statement, by the way, of a mathematician. Right? So somehow the statement is, if you have a mathematical fact, but it's true, but it's not beautiful, then perhaps you haven't thought about it in the right way. Or Dirac, who said it's more important for our equations to be beautiful than to have them fit experiment. Einstein famously said when his theory of relativity was proven by the eclipse, what would you say, Professor Einstein, if the result had shown something else? And you would say, well, I would be sorry for nature because my theory is still true. Because he was convinced by the inner beauty. But there's another point of view, which is here from John Wheeler, the famous physicist from Princeton, which is like a complementary point of view. He said, every law of physics, pushed to the extreme, will be found to be statistical and approximate, not mathematically perfect and precise. So he introduced that the concept of beauty in physics might be an approximate thing. I showed you the Gaussian derivative, the Gaussian distribution at the very first slide, right? That's only true if you have an infinite number of shoes, right? In reality, it will only be an approximate truth. So how do we think of beauty in mathematics? And I would say at least there are two kinds of beauty. The first is universal. So these are concepts that are very abstract. Think of vector spaces, of linear algebra. Differential geometry, I think the work of Ricci would really fit in this. And then there's the exceptional kind of beauty. Now, perhaps you often see mathematicians love Platonic solids. I think many of you have perhaps a little copy of the 5 Platonic solids somewhere in your office. Or you think of a group like the monster group, which is the most complicated, simple, finite group. So we love it because it has this beautiful structure because it's an absolute unique object. It's not generic. It's actually very specific. So what is the kind of beauty that we need in nature? And so there is this kind of, I would say, mathematical Wunderkammer, this cabinet of curiosity, where we put these exotic mathematical objects. And they have a strange attraction. So a good example is Kepler. So Kepler was really fascinated by these Platonic solids and Archimedean solids and these kind of very symmetric objects. And there's a long history. Plato himself has this kind of standard model of nature. He said there's these 5 Platonic solids, and they correspond to the 4 elements. So the cube was obviously Earth, because you can build some solid structure out of it. Fire is a tetrahedron, because it has pointed edges, so you can hurt yourself. Water is an icosahedron, because it is most round, it can flow. And then the 5th was the dodecahedron, and it was like, in his sense, because it was left over, this was the element out of which everything outside the world, so in the universe, was made of. So Kepler was fascinated by the same thing, and most of you must have seen his first cosmology. He said there were 6 planets at that time. There are 5 objects, so obviously 6 is 5 plus 1. And so he made this planetary model. He said if you fit the 5 solids inside each other, you get inner and outer spheres, and now you can calculate of how many ways that can be done. It's a tricky calculation because some of the solids have the same symmetry group, but you find there's a finite number, and one arrangement came pretty close to the ratio of the orbits of the planets. By the way, Kepler was a young man, so this was his theory of everything. Now, of course, it failed. It failed in many ways. There are more than 6 planets. There was no theory behind it. But the good thing is, not that it failed, but that he made it fail himself. So, because he discovered that orbits were not circles, but ellipses. So when he actually found this result, he wrote to Tycho Brahe in Denmark, and he said, you know, it's though I've sinned with the oval, so the ellipse. It's like being punished for leaving behind one barrow full of shit, although I've cleaned the rest of the Augean stables. So he felt he had finally a theory of the heavenly bodies, so he cleaned up a lot of messy physics, but at a cost. The cost was to lose the perfect shape of the circle and include the ellipse. So he felt that he lost a lot of sense of beauty. Nowadays, we know that all Newtonian orbits are actually conic sections. And the real symmetry group operating in Newtonian mechanics in a 1/r squared potential is actually a symmetry group SO4. So it's 4-dimensional rotations actually. You know, it's not 3 but 4. So there's an abstract symmetry group here. So now we would say there's even more beautiful symmetry, but it's not obvious in the way that Kepler made. So how about physics? Where do we see beauty in physics? So here I would say again there are two complementary points of view, particle physics and condensed matter physics. So particle physics, they like to say, they say beauty in garbage. So garbage is the physical world around us, it's very complicated, it's a big mess. But if you zoom in the elementary particles that make up this garbage, you find the standard model of elementary particles, 17 particles with a few lines of equations that describe everything. So according to this point of view, the ultimate beauty, the ultimate laws of nature are found at the microscopic scale. Condensed matter physicists have exactly the opposite. They say, well, you produce beauty out of garbage, not inside garbage. So garbage is the complicating life around us. So the incredible amount of small particles, interacting. Think of just the air in this room, the 10 to the 24 or more molecules that are bouncing, etc. That's a big mess. But out of it come beautiful equations. The equations of thermodynamics that are very, very simple. The equation of hydrodynamics. The collective behavior of complicated objects. So they would say, no, it's exactly the opposite. Real beauty is found at the highest scale. It emerges out of great complexity. It's not underlying great complexity, it's at the other end. So the good thing is, at least it's a symmetric point of view. Each field feels that the other field is garbage, and vice versa. But there are two kinds of beauty. And I want to come back to this theme. Now, we said that in the time of Ricci, Curbastro, and Einstein, there was an incredible, powerful interaction between physics and mathematics. You might say it's really one of the high points of this dialogue. But this evolved in time in a very different way. If we go to the 1960s, we saw that mathematics and physics were moving in opposite direction. Mathematics moved away from applications. It's the famous Bourbaki school, which became very rigorous, very abstract. The famous motto of the Bourbakians were, structures are the weapons of the mathematician. And in fact, they felt that mathematics was tainted by all these applications. So you have to be totally pure, totally rigorous, and don't care about the world around you. And actually, physicists were giving up the idea that there was a mathematical basis of nature. You see, when there were a small number of particles, it was fine. But in the 1950s, 60s, the particle accelerators found thousands of particles. And it was just a big mess. Although there was a simplicity of electrons and protons interacting in quanta of light, it turned out that it was just garbage. And interesting, I think, this was in the 1960s, and this was actually in Berkeley, which was the center of hippie culture, etc. So there was like universities went through this movement of being more democratic and students having a voice. The thing is, the aristocratic structure of atomic physics, as one of the proponents said, is replaced by the revolutionary character of nuclear particle democracy. Every particle was equally valid. So they should receive equal treatment under the law. So there were no fundamental particles, there were no elementary particles, we were all equal. And basically, physicists gave up the fact that there is a fundamental set of equations governed by a simple set of building blocks. And this is in the education. I will come back to Wheeler and Feynman many times, but this is in 1966, and Wheeler invites Feynman, just got the Nobel Prize, will you come to, I want to organize this meeting where, physicists and mathematicians will interact, and we'll see, if there's some things that you can share, etc. And then Feynman answers, I'm not interested in what today's mathematicians find interesting. Period. And I think that's really a statement about the kind of non-communication that was happening at that time. So this spirit was captured by Freeman Dyson, one of the most famous mathematical physicists, long-term treasure at IIS in Princeton, of course, and in his Gibbs lecture in 1972, he wrote about, the lecture was titled Missed Opportunities, so opportunities where physics and mathematics could have interacted, including his own work. He said he's acutely aware that the marriage between mathematics and physics, which was so enormous fruitful in past centuries, has recently ended in divorce. And I love the quote of Beltrami in the early lecture, which also talk about the divorce between math and physics. So in the 19th century, we were equally complaining. It's kind of interesting. So there is some repetitive nature of this dialogue. But I find this really famous because 1972 was really the moment, I would say, when the marriage clicked again. And when the new Renaissance happened, and the last 50 years has seen a tremendous amount of interaction between physics and mathematics. So Freeman Dyson was like entirely wrong. He was very correct about the past, the immediate past, but not about the future. Because I would say this kind of black box theory that physics was attending, that, the S-matrix theory, you cannot know what's inside nature. The only thing you can study, you have something coming in, something coming out, you study endlessly the patterns, but you will never be able to open the box. That was the S-matrix theory, was wrong, because not only could the box be opened, but inside was this very tiny formula. So here I use the power of mathematical notation to write the standard model of elementary particles. So it's describing all the physics you see around you. I haven't included gravity here. I use very shorthand notation. But still, it's interesting that you can give a lecture to mathematicians about this equation, talking about the elements in the equation, and mathematicians will appreciate it. It's the natural language of differential geometry and topology. So somebody like Ricci would really appreciate, I think, this equation and could understand it. Perhaps not how it ties to the description of reality, but the fact that it's there. And of course, the way to understand this is that this complicated way quantum mechanics works is not, there's not like one process. In physics, we think of reality as being composed as many possible trajectories. So if two particles in, two particles out, they could just go straight on. They could exchange a particle, they exchange two or three, or something much more complicated. And to each of these processes, the rules of physics will associate a number, the quantum probability. So we had this interesting situation in the early 1970s when physics was going through this explosion. And very much like Einstein and Ricci Curbastro, it turned out that both were studying the same phenomena. So there was a famous seminar in Stony Brook, which was jointly organized by Jim Simons, the chair of the math department at the time, and Xian Yang, the chair of the physics department. So Xian Yang passed away last week at age 103. Quite an amazing moment, by the way, in the history of physics. And they started this seminar, and they published basically a dictionary. It turns out what physicists were describing as gauge fields, well, they were connections on principal bundles in mathematics. What physicists called the field strength, they were calling the curvature. So there was like a beautiful dictionary between the two. Interesting is, you see there's sometimes a question mark, so there's certain symbols. It's like you translate English to Italian, and there are probably words in Italian that do not have an English equivalent, and vice versa. But they published this dictionary. And the dictionary is actually the metaphor I want to use in the rest of the lecture. Because, mathematics also speaks at least two languages. I think, we have the visual aspect of mathematics, which is, the geometry, and I would say the right brain way of thinking of mathematics. And we have the algebraic, more formal arithmetic way to think of mathematics, which is more left brain. Now, if you can prove, for instance, a theorem sometimes by a long sequence of elementary steps, or sometimes by a single picture. And I think, probably I think even the students here, some of them are more left brain, some are more right brain. And physics actually also uses two languages. Notice the language of gravity, of Einstein, of Ricci, which is the curvature of space and time. And then there's the language of quantum, of elementary particles, that I will say more and more. It's about probabilities, superposition. It's an algebraic language. So if you ask the question that Galileo asked, if the book of nature is written in the mathematics, then you can basically ask which particular, I would say, dialect of mathematics is being used. And you see there's like, even in physics, there are two different kinds of mathematics that we involve. And I will explain to you how the two are related. For instance, we see examples where you can take objects from geometry and bring them in the world of algebra. And we'll see this is the concept of quantization, where you take a classical object and you bring it into the realm of algebra and quantum. So modern physics will allow you to translate from geometry to algebra, and also the other way around. We see examples how, and it will come through emergence, how algebra can bring geometry. And I will try to explain this, and I will say there's a kind of a frame now, which I would love to call quantum geometry, and string theory is certainly operating there. That something is doing both at the same time. It's a bilingual theory. So let's move a little bit in the world of quantum physics. So quantum physics, of course, is, very contrarian. There's a famous line that if anybody says he understands quantum physics, he doesn't understand quantum physics. Famous line by Feynman. And quantum is doing several things that are, I would say, counterintuitive to a mathematical mind. So classical mechanics is the movement of objects. It's basically dynamical systems. So it's a set of differential equations that describe how you change, like the movement of a point in phase space. In quantum mechanics, this is replaced by the famous Heisenberg uncertainty, the relation that momentum and space do not commute. And it means that there are two ways to look at the world. You have a Fourier transform that brings you from one set of variables to another set of variables. So when Heisenberg introduced his framework this year, 100 years ago, in 1925, he wrote to Wolfgang Pauli, his friend, and Pauli wrote back 2 weeks after the discovery, and he had this wonderful quote. He says, "Oh, I understand what you're doing. It's like you can see the world with the pi, the momentum I, or you can see the world with the qi, the position I, but if you open both eyes, you become crazy." And that's a very nice view of this quantum particle wave duality. So there are two perspectives, both valid, but not at the same time. This is very, very counterintuitive, right? If you think that you're a particle, you can describe either its position or its velocity and not both at the same time. It means that you cannot visualize quantum mechanics. It means that if you have a geometrical mind, you have trouble. And then there's this quantum superposition, the fact that in quantum mechanics, you, like famously Schrödinger's cat, you can be, the position or the state of a system is a vector, and it can have various kind of components. So one way to think about it, and this is the famous path integral point of view, that in classical mechanics is a whole set of problems where basically you ask, how do you go from A to B? What is the preferred path? There is some action, and you minimize that action. So this leads you to a straight line in flat space, but there are geodesics in curved space, but in general there's some preferred solution. In quantum mechanics, you do something very different. In quantum mechanics, you sum over all possible trajectories. With a certain weight, the weight is a phase given by the same action. And so if you minimize, you see where, or optimize that weight, you will see it kind of peaks around the classical path. But in quantum mechanics, you have to consider all possible trajectories. So the wonderful thing is that this crazy piece of reality, that if I move from here to the other room, I basically can take any possible path, and the path you see me taking is only the kind of classical path. It fits very well with modern mathematics. Because in modern mathematics, you never consider an object by itself. So this is the famous lesson of category theory, the abstract nonsense that mathematicians developed in the 1950s and 60s. So if you have an object, you think of the category of all possible objects. And you don't stop, because you say, well, I don't look at all geometrical figures, but I look at all the relations between those figures. How can I move from one to the other? And then you say, well, I move to consider all relations among relations. And you go on all the way to infinity. And so this is the modern way to look at mathematics. You never look at one specific object. That's kind of the cabinet of curiosities of the 16th century. You consider all of them at the same time and all their mutual relations, etc. So it's a very modern point of view, which actually fits very well by the quantum perspective. So I want to explain this with basically 3 concrete examples. So the first is particles. So in particle theory, I want to connect it to knot theory. So mathematicians in topology try to study all possible knots. So this is a way in which you can make a circle embed in 3-dimensional space, and you are able to deform it but not cut it. And it's also for a long time, it's still to a large extent an open field to categorize all possible knots. So how is this related to physics? And I go back again to Feynman and Wheeler. So Feynman is at this point a graduate student of Wheeler, and Wheeler calls him up in the middle of the night and says to Feynman, I know, well, all electrons have exactly the same charge and mass. So you learn about the mass and the charge of an electron. Why are they all the same? Is nature like a perfect factory that every elementary particle is exactly the same? And then Wheeler says, because they are all the same electron. And so this was his point of view. So this is space-time. So you have space is horizontal, time is moving. And think of a particle that's not only moving up in time, but it's allowed to go up and down and up and down and up and down and creates this big knot in space-time. What does this look like? Well, here I look, I see a single particle. But if I look in the middle, I see many, many particles, because it's the particle coming up and coming down. So particles and antiparticles. And so Wheeler's point of view was, well, if the whole world is a single particle going up and down in time, now clearly it has the same property, because it's the same person. If I was allowed to travel up and down in time, I could go up, go back, and enter the room here, and there would be 2 copies of me, and they would be, of course, would be identical, but it could be the same me. It's quite a clever idea. So Feynman really says, why aren't there equal amount of electrons and positrons, which is a clever remark. But of course, this led to what we now call Feynman diagram. So he explained that this basically led to his Nobel Prize. So in fact, you can have something more crazy. You have these kind of diagrams. So this is a particle and an antiparticle being created out of nothing and then annihilating again. Or if you wish, it's a particle going up and down in time forever in an endless loop. This is possible. In fact, it's happening right now in empty space around it. It's the so-called vacuum fluctuations. It gives energy in space-time. It's called the Casimir energy. You can measure this even. So now this is the application to mathematics. So here you have a particle going up and down. Hope you appreciate my homemade PowerPoint presentation here. It's going up and down in space and time. It's making a knot. And the laws of quantum mechanics will now associate a number to this, which is the quantum probability of this process happening. In fact, you get many numbers, because just like any other theory of particle physics, you can have the electron going, or say a quark going around. It can exchange 1 gluon, it can exchange 2, 3, 4, and for each so-called Feynman diagram, you get a number, which is actually a knot invariant. So by studying essentially all theories and all diagrams, mathematicians have essentially solved the knot invariant problem using this way. They're, in fact, good enough for Concevis to earn a Fields Medal. So but it's kind of remarkable that it's this intuition of studying all diagrams at the same time that leads to an infinite set of invariants, and that you need, because there's an infinite set of independent knots. Let me go to a second example. It's an example from string theory. So I start with this beautiful object. This is the famous quintic threefold. So the equation you see downstairs is a very simple equation. It involves 5 complex variables, and you should think of it in projective space. So it's not a four-dimensional, but a complex three-dimensional manifold, so 6 real dimensions. Very difficult to visualize. And what you see here in front of you is a lower dimensional version. It's in fact the ones where all the 5 are replaced by 3s. But you know, it's a very complicated geometry. And mathematicians study this space. And one of the questions they have, which is something going back to the 19th century, is can you count curves on that space? So what do I mean by that? So to offer you one equation, so we have the 5 variables, x1 to the x5. Each of them is a single polynomial of a single variable z. So we have a one-dimensional curve on this three-dimensional space. And the curve can be given by a polynomial of a certain degree, and you can do this problem for degree 1, 2, 3, etc. So there's an infinite set of mathematical questions. That number is now called the Gromov-Witten number. So if you do the first one, which is d equals 1, you count straight lines on this curved space. So it's quite remarkable they exist. They're isolated. And any good algebraic geometer knows there are 2,875 lines on a quintic manifold. You should know it by heart. So this is a famous calculation done I think in the 19th century. It's quite difficult. You have to perturb it, etc. But you can count it, so it has a nice number. So if you go to the next, you go to conics, so quadratic equations. There are already 609,250. You easily see the number grows exponential. This was an equation done in the 1980s, state-of-the-art calculation. Really, really complicated. So this is a problem that really grows exponentially in complexity with the degree. So this is the number of cubics. So 370,206,375 cubics. So it's a nice story of this calculation. It was done by mathematicians, and they had a slightly different number. In fact, it was not done spontaneously. Physicists asked them, can you also compute the number of cubics? So they did, and they got a number. And then the physicists say, can you have another look at your calculation? There might be a mistake in it. And the mathematicians looked very carefully, and indeed there was a mistake, and they found this. So they said, no, now we know the right number. And then the physicists say, yeah, that's correct. So what happened? The physicists had all the numbers. So this is quite shocking if you're a mathematician, right? Because you feel this is a process that basically you need a new century of techniques to go one step up, and you get everything at the same time. So what did the physicists know that the mathematicians failed to notice? Because this clearly becomes more difficult if the equations become more complicated. Well, they were thinking in terms of physics intuition. So if you have a string, it's this kind of moving one-dimensional object, according to the rules of quantum mechanics, it does everything at the same time. So there is a quantum mechanical amplitude that is the grand sum of all those numbers. So you put all those numbers in a single function, and it's calculating something that is a physical property. So that's step one. And then you need some magic. And the magic was the following. The magic was people looked at those manifolds, not the quintic, but all so-called Calabi-Yau manifolds, so these three-dimensional complex manifolds. And they made a plot, and they noticed a symmetry, that for any manifold of a certain topology, there was another one that had like the reverse topology, where some of the numbers were interchanged. So they call it a mirror image. So they came in pairs. So for every manifold, there was a pair. And then they studied the symmetry between those two manifolds, which is called mirror symmetry. It turns out that this very difficult calculation on the first manifold became a classical mathematical calculation on the other side. So this was the equivalent of particle-wave duality. Now looking with the left eye or the right eye, but now for this very complex piece of mathematics. And so the conjecture was that these very difficult calculations that have all these ingredients, all these counting numbers, can be kept by a single period integral. And if you believe, so to say, this physical intuition, because it was nothing more than intuition, You could easily prove this, and you get these numbers. And the fact that the numbers checked, at least the first few, was very convincing. And now, in fact, this is proven. So this list of numbers is now a mathematical fact. So again, quite magical. And you already see the theme I'm building up. Basically, I'm asking you, if a mathematician was a quantum particle, if a mathematician had the same kind of intuition as an electron, what kind of mathematics would this mathematician do, right? If we had to leave our classical intuition of space and time and movement and replace it by this bizarre world of quantum physics, which actually is our reality as far as we know, what kind of mathematics would appear? Would clearly be very different and very deep. And we see, I would say, the first moments of this intuition realized with very powerful results. It looks like you have this magical ingredient where you can solve a whole bunch of problems at one stroke. The third example is a little bit more complicated, and I will be sketching it a little bit more intuitively. So it's about quantum gravity. So I told you about strings, these curved one-dimensional object moving in space and time, but there's also something called open strings. And it means you look not at space-time, but in space-time with a certain submanifold in it, a so-called brane, and it has the property that the string can end on the brane, a so-called open string. And if you do the formalism, just as the closed strings lead to general relativity and gravity, these open strings lead to gauge fields, and I would say kind of the language in which the elementary particles are typically described. In fact, you can have a set of those branes, and you get a non-abelian gauge field. So, for instance, quarks have three colors. They're described with a 3x3 gauge field, a matrix, 3x3 matrix. And in this visual depiction, it would be three of those sheets that describe the physics of quarks. Now, if you follow again this kind of logic, so you study this physics intuition, which becomes even more difficult to explain to mathematicians. But physicists say, well, if you have enough of those branes, so think of it, you put a lot of heavy objects there in space-time, they will kind of collapse, they will form, think of it intuitively as a black hole, and they will start curving the space-time. So the physics intuition tells you that there is a way in which the behavior of a large number of gauge fields is equivalent to studying curved spaces. Now, there's an elementary example for this, which I like very much, that at least give you a sense of this intuition. In fact, it goes back to Wigner. So Wigner, in the 1940s, was studying nuclear physics. Now, nuclear physics is very complicated. Now, you have a very difficult Hamiltonian you have to study, If you look at the spectrum of nuclei, it's very, very involved. It depends on a lot of details. So Wigner said, let's forget about the details. Let's do the same thing as he did in the story of the shoe salesman. Let's take a statistical ensemble of these Hamiltonians, of these matrices. So he said, instead of figuring out this very specific matrix that describes the physics of a nucleus, I'm going to do something very simple. I'm just taking a Gaussian average of all n by n matrices. And how does it look like? And he found something remarkable, because if you look then at this matrix, it has eigenvalues, and it has a spectrum. So you can think of these eigenvalues, so some real numbers that describe the spectrum of the matrix, and in a physical system, this would be the energy levels of a nucleus. And he noticed that if you make the matrix size n, that roughly these eigenvalues only grow with the distance square root n. So you can then scale the eigenvalues and say, what will be the density of the eigenvalues if n becomes infinite? And he found a beautiful result. So it's the famous Hove limit. So you send n to infinity, you set h bar to 0, and you keep this combination h bar n, which is the size of the eigenvalue distribution, you keep it finite. And he found this beautiful result that the eigenvalue density has the most elementary shape you can possibly think, namely a half circle. So with particular very narrow and straight edge at the very end. So a circle appeared out of nothing. It's a little bit like the anecdote, like pi is appearing in a problem that is completely statistical. So geometry appears out of a random system. And in fact, it only appears when n is sent to infinity. So in any finite case, you will have discrete eigenvalues, but their statistics will be closer and closer approximated by this circle. Now you can push this theme very far. Instead of having a quadratic potential, you can have arbitrary potential. And what do you find? You don't find a circle, you find actually general Riemann surfaces. You get different kind of topologies, you get different islands. And the shape is, for instance, will be elliptic functions or even hyperelliptic functions. So it's a beautiful mathematical theory. But the overarching result is that you take this algebraic object, which has a degree of freedom, the number of the rank of the matrix or the rank of the system, and if you turn that dial to be infinite, out of this comes geometry. So geometry, up to now, in general relativity, in anywhere, was fundamental. This actually raises the question that, often people say, well, Newton had this law of gravity, but he couldn't explain where it came from. That needed Einstein. So Einstein said, no, space-time is curved, and that gives the laws of gravity. Why is space-time curved? Where do the equations of Einstein, of Ricci Curbastro, come from? Is there something more fundamental? And is it fundamental in the sense of elementary particle physics, at the most deepest nature? Or is it fundamental at the highest level? Is perhaps Einstein's theory of general relativity very similar as the laws of thermodynamics that appear in the limit of infinite complexity? And I would say this latter point of view is the modern view of quantum physics. So you have classical geometry, then you have this funny geometry that I explained to you with mirror symmetry. But perhaps in general we have something called quantum geometry, which should be an emergent quantity coming out of quantum systems. So if this is true, it would actually fit with some other ideas. For instance, black holes. So black holes, I like to call them the atoms of the 21st century. We know they're there, we don't understand them, like atoms around 1900, around 1925, I would say. And they are kind of quite paradoxical, because what is a black hole? From the point of view of gravity, it's literally a hole in space and time. It is the most simple object that we know in nature. It's only described by its mass, and possibly its spin and an electric charge. So typically, there are very few things in nature that can be characterized with one or two numbers. On the other hand, from a quantum point of view, and you think about how much information can be stored in a black hole, it's literally the most complex object, in the sense that there's a mathematical framework to compute the complexity of a black hole. It's called a geometric entropy. It's something coming from Stephen Hawking. And he says, if you think of a black hole, it has an event horizon. Think of it in terms of so-called Planckian length, and that allows you to compute the entropy. And you see that the best storage objects in nature are black holes. You can, in a black hole the size of a proton, or even smaller, you can easily store all the information, or all the digital information that is in this world. So it's this kind of interesting thing that is both quantum and it is classical, and there's this deep question of how does the quantum complexity lead to the physical geometry? And this is this famous topic right now in quantum gravity, where it's usually called holography or complementarity, the fact that in some sense understanding the physical world and the space-time around a black hole can be all captured essentially by understanding these bits, these quantum bits, living on the horizon of a black hole. So I'm not telling you that you should understand this, but I tell you this is a very interesting framework to think. And this again, Wheeler had this view that some of you might have seen this picture. It's in his book, big book, Gravitation, again coming from the 60s and 70s. He had this idea, what he called it from bit. Why is there something around us? Isn't perhaps information the most fundamental thing? And can we somehow think of space and time and nature as being kind of knitted together from little pieces of information. Well, it's a beautiful, of course, drawing, but it's kind of complete nonsense. You know, how can you put equations to this? And I think now we are in a moment where we can put equations to capture exactly this kind of logic. And what we see in many situations that out of these quantum systems, so I think that's my statement. There are a lot of systems, basically large and gauge theories, that if you look at the behavior when this number n, the complexity of the system is become very large, out of it comes gravity. Out of it comes the equation of general relativity. Out of it comes the geometry of space and time. All the beautiful differential geometry that we're celebrating today is coming out of this quantum framework. And that's, I think, exceptionally remarkable. And it tells us something that, you know, perhaps geometry, which I think you might think is the most fundamental thing there is not fundamental. It's an emergent quantity. It's something that appears like the Gaussian distribution of Wheeler and of Wigner. And there are many kind of nice elements of it. For instance, you know, in gravity we can have these famous wormholes, you know, way in which one point in space-time is connected to another through this kind of little tube that goes from one to the other. And turns out that's intimately connected to this fundamental property in quantum physics that two particles very far away can be entangled and can be kind of correlated. So there's a lot of emergent properties of quantum systems that became captured by the mathematics of general relativity. So what makes this interesting from pure math, I would say, is that the right brain, left brain distinction in mathematics. Now, do you like to think in terms of geometry? Do you like to think in terms of algebra? They should be in some sense the same. There should be a dictionary going from one to the other. So if you think of the concepts in geometry or the concepts in algebra, there should be some way to go from one to the other and home and back. And I think that we are only scratching the very surface of this. But I think certainly mathematicians that love to think of the universal quality of mathematics, and as we said, you know, the truly fundamental mathematical objects have many different perspectives. I think this would fit very well with Thurston's description of derivatives, but perhaps, you know, many other objects have this dual point of view. So I would say one of the overall lessons is that geometry, that was, you know, 100 years ago, was absolutely key in connecting mathematics and physics, is now being replaced by kind of quantum information. And this is a whole new chapter, I think, that we are now just developing. So let me finish by going back to Galileo's book. So what did we learn? So we learned at least that it's a little bit more complicated. You know, the pieces of the book are written in mathematics, others are written in physics. Ideally, you would like a dictionary, so it's like to find. So are we now bilingual? And fortunately, we're not. It seems that in a funny way, physics and mathematics do not commute, in the following sense. Physics had led to spectacular predictions of mathematics results. Some of them have been proven. So say Fields medals have been given to this, but not by cleaning up the Augustine stables of physics. In fact, by taking pure math approach. So the intuition of physics seemed to be kind of foreign to mathematics, and perhaps it cannot be captured by mathematics, which is really interesting. And also, if you look at this field, how quantum physics is interacting in mathematics, so it inspires many areas of mathematics. But, you know, it's a kind of a sketchy story. There are various parts of mathematics that are relevant. There's not an overarching framework. So the question is, will there ever be? Now, how do we think of this universe? Is it in terms of an atlas with different kind of maps? Do we cover little pieces of nature with different kind of mathematics? Is there one kind of universal thing? Is there something like quantum mathematics? And what would it mean? What would it be? Obviously, there's a lot of inspiration at this moment from quantum physics. And now I want to end with this image of Plato. Now, so he had this, of course, this famous image of his cave, where we all were tied together, the prisoners. They couldn't see mathematical reality, they only saw the shadows on the wall, the physical shadows of abstract mathematical objects. The Platonic world, that is only, none of us, so remember a famous story that one of my friends once told me. He was a young boy in elementary school, and his teacher says, no, took a piece of chalk and draw a line on the blackboard and say, well, this is a line. It's infinitely thin and infinitely long. Clearly, this cannot exist. And then my friend raised his hand and said, but it can in my mind. And he was sent away from the classroom, which is actually... but there is a mental image where we can have this mathematical reality. But I would say now we're in a kind of an opposite world. We have this physical reality that you might have feel is still kind of very wavy, uncertain. We don't know exactly what the laws of nature are. And what it does, it projects kind of these very clear mathematical shadows in terms of very precise conjectures and results. The numbers I showed to you, they're very precise. Mathematicians can try to check them, can prove them. So very crisp reflections of a very vague and intuitive quantum physics world. So in some sense, these roles have been reversed. But the good thing is that, still a lot of progress being made. I think it's one of the most exciting, intellectually exciting developments of the last 50 years. I feel very lucky that we're living in this time when mathematics and physics are so strongly interacting, that physics has went into a very counterintuitive world of curved space and time, of quantum particles, etc. But mathematics is able to catch up and actually even sometimes improve on physics. So Wigner ends with this quote. He ended on a cheerful note where he says the miracle of the appropriateness of the language of mathematics for understanding the laws of physics is a wonderful gift we neither understand nor deserve. And he said I should be grateful for it and I hope it will remain valid in future research. In fact, he wrote that at the same time when I was born, and I'm very fortunate that my whole life I've only seen this increasing in a very productive way. So thank you very much for your attention.
So, thank you. I'm sorry for my voice. Thank you very much for this wonderful lecture. Now we have plenty of time. If you have any question for Professor Dijkgraaf, curiosity about his lecture, about the relation between physics and mathematics, don't be shy. There's plenty of students here. Just ask your questions if you do have one.
It's always difficult to ask the first question. The second question is much easier.
Easier, yeah.
There's a question there in the back.
Very good.
Hi. I wanted to ask about, you mentioned a lot of analogy between mathematics and physics, but what about the analogies between physics and physics? For example, like the cosmological horizon and black hole horizon, and can we find, can we make physics easier for us by using, for example, lower dimensional physics and higher dimensional physics? Is it also useful?
Are you asking how we can understand all of this? Get intuition for it? What do you...
Yeah.
Well, I think, that is one of the kind of powerful lessons, I think, what we see, in mathematics. So often we think in the progress of science is discovering new things. But I think a lot of progress in science is discovering a new way of looking at something familiar. And the example of how to think about the derivative, I think, is a good example, right? Because all of these are valid points of view. And in fact, if you're studying, you might use all these different images at the same time. So I think, you know, a good question, particularly in physics, is can we develop intuition about this? And we do this by studying, you know, models. So often people ask, why are you studying models in physics? Why don't you're not studying just the real world, you know, you're studying a lot of simpler things to get a kind of an intuition. And I think that's how mathematics works too. You know, no mathematician can visualize a 24-dimensional space. You can only, perhaps some of them can visualize 4 dimensions or something, you know. It's, I know very few of us. Thurston once said he could. But so what you do is you think of simple models, and as a student, I think it's incredibly important. There are a few simple things you fully understand, and then you can almost take that understanding, and if you're in a much more complicated object, you use that intuition. As you said, you know, how do you think about the black hole? How do you think of the cosmological horizon, you know? Nobody can really think in terms of those complicated spaces, but if you have some good metaphor in your mind, you can use that to somehow jump to a more complicated situation. So why are we even sketching figures on blackboards if we discuss very complicated objects, right? Because in some sense captures a piece of thinking. And if you see the progress of physics, often it was this kind of different way of looking at an object. Good example is quantum mechanics. If you learn quantum mechanics, it helps really to first think in terms of Hamiltonian mechanics. Of course, that's what Dirac did with P and Q. That was not the common way of thinking of mechanics. But once you have that way of thinking of classical mechanics, then it's relatively easy to take the step to quantum physics. So often I think it's a very good investment, I would say also if you're a student, to develop your own point of view about a certain object. You build your own intuition, and then sometimes you can use that intuition. I always feel if you have to understand something, just sit and try to figure it out for yourself in your own way, and that might be a completely different and personalized way to understand something, and it will actually be very helpful in the past, in the future.
Thank you.
More questions.
Thank you. I have a sort of a more personal question. Considering your experience in the field, what would you suggest to a new student in physics interested in this field of mathematical physics, which covers, as you've discussed, a plethora of different mathematical theories that can almost get you lost in some way? And so what would you suggest to a student for him to get a sense of orientation in this very complicated field?
Yes, on the one hand, you're quite right. So there's a lot of stuff happening, and you know the question is, where do you start? So my personal point of view is start at something you really love and like. So go to lots of lectures, you know, and you will probably have the effect that I always had. You know, certain things I know they're interesting, but they're not resonating with me. You know, and I wouldn't look forward on learning more about it. Other ones you feel fascinated, you know, and it's not quite clear why, but you just want to understand it. So the good thing is, if you're a student, you can still devote a lot of time trying to understand something that is already known. You know? You're not forced to discover something important yourself, you know, within the next week, something. You know? So you can take your time, and you know, there's this famous saying in mathematics, particularly, that you can start digging anywhere. If you dig deep enough, it becomes really interesting. So there are certain elements in this grand story that look very complicated because all these disjoint examples, and you don't see, there's not a grand unified theory, but there are unifying themes. And one way to get into it is really pick something that you really want to understand, really understand it in your own way, and then start from that point of view. I think it's very difficult to try understand everything at the same time. So just pick one that you like yourself. You say, well, this is something I would enjoy working on. And the good thing here is that with these fields, there's a huge area of mathematics. So one thing that is getting involved in these kind of quantum physics questions, and it seems to have no boundaries. So, there are a lot of fields in math that I thought would never ever be related to it. So one thing that mathematicians do, they take these ideas, they make some of them rigorous, and then they go to the next step. And then even physicists ask, so why are you doing this? Right? Just to give an example, there are certain amplitudes that people compute, and it turns out they come out as integers. Then everybody asks, why is it an integer? Is it counting something? No physics intuition why that should be an integer. But then mathematicians say, well, there's clearly something deeper. So they start digging, and other fields of math come in that might be very, very far removed from physical applications. Might be number theory or something very abstract. But it's kind of fun to explore that. So I think this is a field where just the intellectual freedom to explore is very exciting. And I think the most exciting thing also is it brings different mathematical subjects in contact. So, which is interesting too. So you have many examples where you have these kind of dictionaries, where from one branch of mathematics seems to connect to another one. These two mathematical communities are not in contact because it looks like completely different fields. And then certainly, like for instance with knot theory, you had people studying topology, others studying these algebras. Turns out it's the same thing. Well, that's kind of exciting, Then once you have a dictionary, it becomes really exciting because you can see something be able to translate in something else. And again, you should just take something that you find yourself interesting, follow that, and then I think if you start to pull on that string, many other things will come. Yes.
Let me ask you one thing, and then we get more questions. During your career, you've been working at the interface between mathematics and physics, so you met and worked with many physicists and mathematicians. Is there something peculiar about the approach of mathematicians that maybe physicists should learn, and vice versa?
That's a good question. So I think what physics brings is a certain kind of intuition. So how do you build up that intuition? I think it's because you try to visualize what happened. So it's these, I think I shared some interesting examples. It's like Wheeler thinking of this particle going around, It's somehow try to visualize. Often I think in physics we have certain concepts that are even more powerful than the math. In fact, sometimes it's almost impossible to capture in mathematics. That's also very frustrating. But so physicists bring this kind of intuition, and I would say even in the physics community, there are those who have a more mathematical mind, and others have less mathematical mind, and it's the ones with a less mathematical mind that often are the most innovative because they come with ideas that are completely foreign to the mathematical way of thinking. So I think that's very productive. I think we see the most interesting interaction when you have somebody with a clear physical intuition that then tries to build it into math. In mathematics, I think it's what mathematicians do is really ask fundamental questions. So why is this? What do you mean with this object? And physics easily gets stuck in a particular example. So we explain something, well, for example, this and this and that. And mathematicians are not interested in one example, I'm interested in what is a quantum field theory? What do you mean even with a space with these kind of properties? So it forces you to think in this more broader sense. So physics you might get hung up by saying, well, you know, we had this picture of the mental world, which is much larger than the physical world. So from physics, you might have a lot of pressure to study the little part that connects to reality. Mathematicians are not interested in reality. They're interested in the grand space. So they will ask you, well, but what are the general properties that you are assigning to this one particular object that you want to study? And I think that's a very good way, a very productive way to think about problems in science. So, and I think mathematicians, which I also love, is that they, I think, fundamentally feel there's a unity to the field. So that the various branches of mathematics are still connected to each other, which I think sometimes in physics we have less of that kind of feeling. So I think this idea that anybody should be able to understand everything, also what your neighbor is doing, I think that's also very inspiring.
Thank you. More questions?
Okay, so hello, thank you for the beautiful lecture. My question was, since you previously said everything is physically explainable, and you mentioned our mind as well, it is a biological computer. Maybe this question is a little bit too philosophical, but do you think free will exists? Or we are in a, like everything is explainable by some like physical laws?
So your question is whether we actually physically exist or it's all in our minds?
No, if free will exists.
Free will. Oh, great.
Yes.
Well, I think we're moving into drinks. No, but it's a good question, since you can ask any question. So I think it's very easy to understand that we have the illusion of free will. So it's probably something, you know, I would say emergent. It comes out of, I personally think that our brain is a physical system. It's described by physical laws, by the movement of particles. I think actually how we think is probably not even related to quantum mechanics. It's a very complicated system. And I think our mind at any moment considers many options and has a very complicated way of picking one of those. And that we feel as free will, right? I have to go to the left or to the right, something. But I feel that, you know, in a fundamental way, those processes are described by science. So I think, you know, I would be very, very surprised if I myself would be, or you, would be a part of nature that is not captured by the equations as the rest of us, of the rest of the phenomena. But the question is, of course, what are you thinking and what's in your mind? So I think it's very easy to have a very deterministic system that gives you the illusion that you have free will. Yeah.
Thank you.
On top of that, I think, you know, there's a thing which I find even much more puzzling, and I think all of us should puzzling, is that, of course, our physical reality is described by quantum physics, which has a probability in it. I don't think it's difficult to understand quantum mechanics because we can understand the equations and we can calculate, you know. And there's one part of physics which is the famous shut up and calculate school of quantum mechanics, so just don't ask too many questions. But why is reality like that? So we saw it's extremely beautiful and productive, and it's, from a mathematical point, gives many new insights. But the fact that I can look at a radioactive atom, and I know it has a certain probability to decay, say the next hour, 50% probability, and it decays after 37 minutes and 45 seconds. And why that particular moment? And that in physics we're not able to explain this. I find it very puzzling. So I think there's this kind of uneasiness. Why if nature picked those laws to describe physical reality, why do they have this kind of probabilistic, undeterministic element in it? And I think that's a very deep question, and we see now young people are very lucky because you're growing up with a lot of experiments where you can see quantum physics. No, you can just experience it. You see it proven, all the crazy predictions of quantum mechanics have been proven, Nobel Prizes have been given for it. But there's probably a question, I think, that's still deep inside me, and I think in many of you, why? Why is the universe not described by a simple differential equation? Mathematicians would love that. Why is this kind of funny quantum thing with probabilities? I think we don't have a good answer to it. And it gives us a lot, but it also takes a lot away. We not have a deterministic system. We cannot explain everything in exact numbers. We can only describe the world in terms of probabilities. It's a very powerful language mathematically, but it's also, I think, very frustrating. So I think one of the big puzzles for you and your generation, so it's now 100 years since quantum mechanics was discovered, but the question, why did nature pick quantum mechanics? Why is that fundamentally our description of reality? I think that still has to be answered.
There's a question there.
It's a question that asks you your opinion about many attempts that were made in the last decades to unify the gravity force with all the other natural forces that have already been unified. Why, in your opinion, maybe also in the others' opinion, that hasn't happened yet? To explain my question, the way I understood the general relativity, it was developed, it's a successful theory, it was developed because there were advancements in mathematical techniques pioneered by Ricci Curbastro on a side, and others. And because of new ideas in physics brought about by Einstein, like, for example, I'm trivializing, but it's just to make my idea clear, the constant value of the speed of light. Okay, so using mathematical techniques, improvements, and new physical ideas, there was this new theory, successful theory. In your opinion, the unsuccessful attempts along these decades of unifying the gravity force on a side and the other natural forces on the other are because it lacks some new technical mathematical advancement, or because it lacks some new physics idea, or both? Your opinion and the
I think the brief answer, both, in the sense that, so I would say we have been successful in a theoretical framework in certain elements. So string theory, for instance, gives examples of theories that are both describe gravity, quantum, in a quantum way, and elementary particles. The question is, does it fit the reality that we see around us, this particular, the standard model of elementary particle physics? So I think we have some frameworks, but I would say even the mathematics that brings that string theory and that framework is very limited. So it basically also looks at gravity as if it was a theory of particles, so the graviton and how it interacts. But gravity brings many more questions. So it brings questions about cosmology, of curved spaces, and simply the language, the mathematical language, is not powerful enough at this moment to explain. So I would guess that what we need is, I think we are on the right track, but what we need is more powerful mathematical ideas. As I said, there are elements of the mathematical theory, but they're not unified, so there's no universal mathematical framework. But I think we also need more physical ideas. These are very deep conceptual questions. So if you think about cosmology, you have to ask the question, how did the universe come into being? Now, all of science is about essentially understanding, how how a particular state of a physical system evolves in time. How can you, this was the problem that Einstein had, how can you, say, have a cause, how can you have a consequence without a cause, etc. So it means that you have a different framework to think about science. So I think there are actually cosmology and gravity, whether it's black holes, etc., give very deep conceptual issues that do not fit well in the way of thinking about particle physics, which is much more constrained view of the world. And then you see that just the language of mathematics is not powerful enough. And I think what kind of exciting, or what I was telling you today, so these are, I would say, model questions where we have math and physics interacting, and we just develop new mathematical concepts and language that I think are really new and are very deep and need to be further explored. And they also give deeper physical ideas. For instance, the fact that geometry of space and time might not be a fundamental thing, might be coming out of another system. So I think these are good ideas, but we lack just the powerful mathematical tools and physical intuition to answer them. Which is kind of exciting, because it means that, if you're a young theoretical physicist, there's a lot of open problems that, could have major breakthroughs.
There was another question there.
Good afternoon, Professor. Forgive me if my question is perhaps too abstract or too vague in regards to the matters discussed, but seeing how the connections between physics and certain mathematical calculations has been made, I wanted to ask whether there is a possibility in the given physics of our time, as much as they are being developed, in physics being used to determine mathematical proofs as well, perhaps linked with such matters as the Millennium Problems, or whether there is a formalism or axiomatic reasons for which physics cannot be utilized in these terms.
I think that's a very good point. So the question was, is some of the physical ideas can be made precise enough to make mathematical proofs, right?
Precisely.
So the example, for instance, of mirror symmetry is not like that, because it was proven, but it was proven entirely on the mathematical side. So the physics intuition was too difficult to do. I think, I truly feel that connection is not just a suggestion. There should be a real solid bridge built. So yes, I think it could be done. And there are examples. So for instance, one of the millennial problem that was proven was the Poincare conjecture in 3 dimensions. And if you see how it was proven by Perelman, a lot of gaps, but he was given the credit. It was about flowing, so you take the geometry and it flows under a set of equations. That's entirely physics. In fact, it's the renormalization group flow on certain sigma models. So the equations and all of it, the intuition was coming out of physics. Then you have to work out the details. But it was not something completely new. So I would say that was a physical intuition made precise. And I think there are many, many other examples where you can do that. Of course, it could be also the other way around. So, there's a millennial problem, which is basically asking to make rigorous the physics of 4-dimensional gate theories. Very few people are working on it. Unfortunately, it would be very nice to get a proof. So I think that is something where perhaps the math should be developed to prove, which is essentially a physics conjecture. No, I think there's a great, and the nice thing is that if you can make a piece of physics more precise, it will be a very powerful tool. And we know of examples. For instance, quantum mechanics was made very rigorous, so von Neumann and others. So the whole theory of algebras, C-star algebras, there's a whole formalism that was developed in the 1920s, 30s, 40s, that made the rules of just quantum mechanics completely mathematical rigorous, and that was very powerful and was able to prove many things. So there's this whole debate, why would you, if you're a physicist, why would you need mathematical proofs? Who cares? And I think there are good examples of things where the intuition of physics leads you to the wrong direction. So there have been some things that most physicists were true and they were not true, because you find a counterexample. Or the mathematical proof, like you want to build something and you build this big scaffold, all this artificial structure, and then it turns out that the scaffold is more important than the thing you want to build, right? You build a framework that then can be used for many other ways. So there are many examples. So again, when people want to make particle physics rigorous and prove renormalization group theory, that was very good. It worked for the standard model, but then it could be applied to many, many other areas, even in condensed matter and statistical. So sometimes you develop very, very powerful tools by proving one particular theorem. So yes, I think, I find it very unsatisfactory that there is physical intuition that leads to results that we know as true, but our logic is not rigorous. We can't make the logic rigorous. I think it's kind of unacceptable. But it's pointing to, fundamental points. So most of physics uses quantum field theory. Any course for any physics quantum field theory, there's essentially no, and most of them are gate theories, right? So one of the millennial problems is just prove that the most standard tool in physics exists mathematically, in a rigorous way. So it's not yet proven. So physicists say, well, we don't worry about it because we only use it in a certain approximation. But they should worry about it. If that's what you get taught in class, it better be rigorous at some point. So I think it's important that we make this intuition precise. Yes, people should be encouraged to work on it, I feel.
Thank you very much.
So, thank you for your presentation. I was wondering if you think that philosophy of mathematics and philosophy of physics can play a role in understanding the relationship between mathematics and physics. For instance, some of the questions you raised concerning the nature of mathematical objects are questions that we find in the domain of philosophy of mathematics, and exactly and sharply boil down to the difference between the ontology and epistemology of mathematics. So I was simply wondering, what do you think about this?
I think that's a very good point. So I think one of our losses in the past decades is that, quite generally, I think in the sciences, philosophy of the sciences and history of the sciences were kind of almost lost. You saw very few, I don't know about here, but in many universities they don't give a prominent role. And I think actually you see a resurgence of some of these philosophical questions, I think. And by the way, the same is true, I think, for the historical questions, right? Because understanding these long-term developments, it's really, I find it very inspiring to see how in the past people struggled with this, right? They sometimes ask bigger questions than we do right now. So this kind of shut up and calculate philosophy, I think, is very narrow. The interesting thing is with quantum physics now so be central, it asks many deep philosophical questions. So it becomes now an integral part of what it means to do physics. And I think in mathematics too, I think that you see, again, much interest in the philosophy of mathematics. It's a completely different topic, but if you think of the role AI is playing and will play, again, it goes to the core. What does it mean to be a mathematician? What does it mean to understand something in mathematics? So I find it very inspiring that these fields come back. And I think this is an important part of the richness of studying math and physics, to have those philosophical issues, whether you worry about what is the universe, or what is this mathematical universe, or what is this mental universe. And again, you know, the nice thing is that some of these things become very practical and they can be measured. You know, you can ask philosophical questions and there are neuroscientists telling you how your brain operates. You can ask deep philosophical questions in physics, and there are experiments you can do to check some of these strange predictions of quantum mechanics. So I think it's very exciting, and I think, you know, if you think of the curricula, I would say, you know, it's history and philosophy should again be connected to studying our domains, because they're an integral part of, I would say, the tradition of our fields. And this was very natural in the times of Galileo, etc., or perhaps even the time of Ricci. I think it should be more natural for us. I think we have become a little bit too kind of specialized and too practical oriented in our studies. Do not ask these questions, and I know at least many students I speak to have these kind of questions, and it's kind of wonderful to study them.
Maybe the last couple of questions. There is one there and one here.
Good afternoon. I would like to ask, what do you think about artificial intelligence in mathematical physics? Will it soon play an important role in developing new techniques?
Can you repeat? We cannot hear very well here.
Yeah, so what in mathematical physics?
Artificial intelligence.
Artificial intelligence. So again, that's a big topic.
If it can replace us, I guess.
Sorry?
If it can replace us.
Yeah, so, you know, I think it's really exciting for all of us that we live in a time when at least, you know, machines are doing some of the things that we do. I feel if I talk to my colleagues, there are three possible answers. So one is this will give a renaissance and a boom in math and physics. The other is that this will be the end of mathematicians and physicists. And the third answer is it's business as usual. And I think, you know, all three options are on the table. I think in the short term, I would say it at least shows what is the strength of human intelligence in those fields, because the mechanization of mathematics, it's underway. Now you can make machines do formal mathematics step by step. You know, think of possible theorems and prove them. So you explore this vast universe of possible mathematical statements. And it's really infinite in a very deep way, right? You can think of all possible interesting mathematical statements that you can prove. I think actually you could easily get lost there. And so what I think in mathematics is important is to have some intuition where you want to go. One of the lessons I think of my lecture is one of the great teacher of intuition is reality, is nature. You know, it's telling us a little bit of a certain kind of mathematics that's very deep, that has a lot of potential. So the really important things in mathematics often come from nature. As I said, you know, from differential equations to symmetry groups, because we see them around. It's the natural language of nature. So I think, you know, artificial intelligence could easily be completely lost. So I feel it's like a ship with a very powerful engine, but, you know, you still need a human being to be a captain on the ship. That would be my brief take.
We have talked about the relation between mathematics and physics, and I wanted to ask you, what do you think about experiments? Because experiments are very important in sciences, and in some fields there are no experiments to prove certain theories. For example, in quantum gravity, one of the main problem of theories about quantum gravity is that there are no experiments to prove certain theories. So what do you think about experiments, and what do you think about the theories that maybe cannot be proven experimentally?
So first of all, experiments, of course, incredibly important in physics, right? Because we're talking about physics not as an abstract field, but describing reality, nature. And we know that with every experiment we learn more. And we also know that human beings are very bad in predicting where nature is going, right? So many experiments has shown us results that we didn't see coming. So particularly in fundamental physics, like particle physics, we have a few hints. We have built these big, accelerators, etc. It's incredibly important. We keep pushing this. On the other hand, what we see is that these days, I would say you can almost do the other way around. So you can say, can we build materials, for instance, that have certain properties? So we are now in a stage where we can make like quantum materials, arrangement of atoms, and which have the most magical and properties. So we know of a few of them, like superfluidity or super, But these days, I would say you could almost do the other way around. So you think of a law of nature, and then you ask your experimental friends, can you build a material that has these properties? And can you check certain things? So the wonderful thing is that in fundamental particle physics, we have all these crazy things as, gauge fields and electrons and particles with all kinds of spins, etc. In condensed matter, we have the same phenomena. However, they're not fundamental, quote unquote, they are emergent, so they appear on the other end. But it's the same theoretical physics. It's the same equations that are describing them. So perhaps we're looking for like Majorana particles in perhaps neutrinos or Majorana particles. But people in topological superconductors, they are in the lab, they're producing these quasi-particles that have the same property. They're also hunting for Majorana particles. It's not quite clear who will find it first. So yes, experiments are very important, but certain elements of this theoretical framework can be tested in the lab. So sometimes you read things about black holes tested in the lab. They didn't create a little black hole. They created these quantum systems that under certain circumstances start to behave like quantum gravity, right? So in somehow you can engineer very complicated systems that have fundamental laws of nature that might be completely new. So even as a theorist, you're not only depending on the phenomena that nature has created for us. No, our experimental friends in the laboratories can build things that have completely new theoretical frameworks. So some of this you can test, but not in terms of the fundamental laws of physics, but using these quasi-particles and emerging quantities in quantum systems that people can build. And here again, we're just at the tip of the iceberg, right? Only recently, with techniques and nanomaterials, etc., we're able to build these very exotic materials. So for instance, in mathematics, sometimes we have these lists of all possible symmetry groups, like all possible wallpaper patterns, etc. So there's certain properties of materials where this very abstract mathematical frameworks led to a list of possible materials. So mathematicians show that there is only that many options. And then now people are in the lab trying to find an example for each possible mathematical law. So I think that's incredibly exciting. So some of these very abstract mathematical things, for instance, things I worked on like 35 years ago, I thought it was pure math. Now people are doing it in the lab. They just find the materials that display all these kind of funny things that we were describing. So if you take the experiments in a broad sense, not only the ones done in particle, but in cosmology, in gravitational physics, in condensed matter physics, in atomic physics, perhaps another area, perhaps in artificial intelligence, etc. Then it becomes a very exciting mix of theory, experiment, simulation, and in the end also of mathematical theorems.
So I'd like to finish asking you another question, since we have many young students here. No? We heard before a possible advice for a physicist that he should study mathematics, then more mathematics, and then again. What would you say to a mathematician, for instance, to a young mathematician, or again, if you have a different advice for a young physicist?
Well, I think, it shows that if you are bilingual, it actually is very productive. I like to say, the best way to get a good idea is to steal it from your neighbor. So as a physicist, you can steal ideas from math, and as mathematicians, you can steal ideas from physics without, having to build it up from the ground up. And I think, that advice of Galileo, of Sommerfeld and others, to study as much in the languages of science is incredibly productive. But I would say, for all of us, I think, one big lesson is that we are in a time when it's very tempting to be very specialized and very narrow. And I think this is really an issue because, one of the remarkable things of science is that you have ideas that translate to many different fields. We saw a very simple example was the derivative, right? You can apply it in statistics, in discrete mathematics, you can apply it in knot theory and differential equations in all kinds of fields of geometry. So it's a wonderful, it's like a tool that you can use in many different ways. So my advice would be, if you're a young person and you are able to learn kind of a second language, go to a field which is very foreign from what you're doing. This might be incredibly inspiring. So if you're a mathematician, study areas which it could be physics, it could be neuroscience, it could be computer science. Actually, I think we're living in a time when it's much easier to connect the various kind of domains in science. And I think honestly, sometimes I feel that science is a little bit like plate tectonics. So you will have these domains, and when they hit, you get a lot of volcanoes, and it's very exciting. New islands pop up. So I would say, whenever you're in a certain field, go to an area where it's hitting another field, because it's like a lot of excitement.
Well, Professor Robbert Dijkgraaf, again, thank you very much. And thank you all for being here, of course, tonight with us.